Hello, everybody. We are going to be talking about a project that we undertook at Google in the beginning of this year as part of a hackathon. And Robert had the idea that we could try to put his words into action and build a new SDK from the ground up with a small team in a short time. This is something that we've wanted to do since I joined Google several months ago, is expand Beam's SDKs. And we thought TypeScript would be an interesting choice. So we assembled the team you see here and worked for one calendar week and maybe a little bit of a weekend to put together a TypeScript SDK. And the impressive thing is that we were able to accomplish just that, have a functional, minimal SDK. There might be a few caveats about exactly how functional it is, but we showed that you can do a lot of work in a short amount of time. And I think the credit to that largely goes to Robert, who's thought about this problem for a long time. Next slide. So a good question is, why did we choose TypeScript? Why do we think we need a TypeScript SDK for Beam? Next slide. Well, one reason is that though we have SDKs for Java, Python, and now Go, as well as Scala, we haven't ever addressed JavaScript, in spite of the fact that JavaScript is the most popular language amongst developers. And so we see here the results of survey saying, what is your normal usage of different programming languages? And we see that JavaScript stands head and shoulders above all others. And yet we weren't supporting this. Now, another interesting point is that TypeScript usage has been steadily increasing. And so I think if you ask people, do you use JavaScript or TypeScript? The answer would usually be both. So those are an overlap. And TypeScript is more amenable by far to the Beam model than untyped JavaScript, which would present many more challenges than even us having a wrapper like TypeScript that allows us to use typing. Next slide. And also TypeScript is a prime target for adoption. This is showing the response to if you were to migrate, are you planning to migrate to another language or framework? And you see that TypeScript has strong adoption across a wide variety of languages. Next slide. Go also has a lot of people who want to migrate to Go. We've already started and have made incredible progress on our Go SDK, which is now in preview release on Dataflow, as well as fully featured for batch workloads on Spark or Flink. So I invite you to check out the Go SDK. It's still under very active development, but I'm very proud of the amount of functionality we've added to that in the past few quarters. Next slide. So finally, it's a way to demonstrate one of the fundamental Beam principles is that Beam is portable. So if we can show that even something as foreign, perhaps, to the innards of Beam as TypeScript can be developed into a functional SDK, and that we can also use that to show the updated ideas of how to build an SDK and show that you do not need to like mindlessly copy the patterns that are in Java or Python. We can actually present a new SDK that's fully functional, but adopts some different paradigms. Next slide. And now I hand this over to Robert, who, as I say, led the team through this effort and has been thinking about this problem for a long time. Thank you, Robert.
So what exactly is, what exactly is a Beam SDK, TypeScript or otherwise? And so when you ask this question, there's several components to what makes an SDK. So the first is an SDK is the tool or library that lets the user author Beam pipelines. So it's really what the user interacts with. When they sit down at their computer and they put their hands on the keyboard, they're interacting with the SDK, and the SDK defines kind of the pipeline that they're trying to run. The second component of the SDK is it's the thing that translates it into a form that can be submitted to a runner. So we have the idea of Beam is you have this plethora of runners. We have Spark and Dataflow and Samza and Flink and a direct runner, and we want to be able to run our code on any of these runners. So the SDK is the thing that turns the user's intent into something that the runner understands. And then lastly, the SDK, an essential part of the SDK, is it allows you to package up the user code and run it remotely. So many of these runners, in fact, all but probably the direct runner, are really tuned to be able to run on, in a distributed way on remote computers, in a data center, in the cloud. And in order to run the user code, you need to be able to package it up, send it through the runner, and then execute it in an efficient manner on a remote server. So these kind of parts are the essence of what an SDK is. There's another definition of the SDK that I like, which is it's really an idiomatic interpretation of the Beam model for a specific language. So you have the Beam model, which has the notion of grouping and mapping operations. And you say, how do you map that onto a specific language? And we had Python, we had Java, and we had Go, and they all kind of like take different twists on it. And every time you throw another language in there, I think you reveal something about what is kind of essential to Beam versus what is specific to the language. And you want to do this in a way that is both amenable to executing in a parallelizable way, but also fits naturally in with the language. So let's look specifically at TypeScript and some of the considerations that we had when we're developing an SDK. So the first thing, which is really nice, is that functions are really first-class objects. And even more so than probably any of the languages we've dealt with so far, the kind of mindset of JavaScript and TypeScript developers are that you create these functions, you pass them around, you create lambdas. It's just a very natural thing to do in TypeScript compared to Java or even Python or Go. The other thing that TypeScript gives us is it gives us a very powerful typing system. So we can have p-value is this recursively defined type, which is really nice. Despite TypeScript having a very powerful typing system, that is just entirely used to generate the JavaScript underneath, and then all the typing information is gone. So you have almost no typing information at runtime. I mean, you can kind of do is instance checks, but it's not the same. You don't have, polymorphic dispatch or anything like, well, you do have kind of a class hierarchy, but you don't have, function overloads and all that kind of thing. So it's kind of this, very powerful in the front end, but almost nothing in the back end. Another thing going for TypeScript and JavaScript is everyone knows JSON, and it's widely used. And it lends itself to more of a schema-first relational approach. So rather than having like KVs and lots of coders and user-defined types, we just use JSON objects all over the place. And this is, we want to be more efficient when we cross serialization boundaries, but it means that we can have more natural kind of ways of grouping things. I'll get to exactly what this means later. This is a direction that we're trying to take Beam in general. Some of the downsides is that async calls are contagious. And this is by design in JavaScript, that if you ever have to wait for something, they want you to await it so that the single threaded model can go and do something else while you're waiting for your result to come back. But this kind of makes it so that every single kind of thing that you might want to do synchronously or asynchronously really has to have kind of like two methods. And if you ever do anything asynchronous, it's contagious and bubbles all the way up to the top. There's no way to actually block waiting for results. And then the other kind of really interesting thing is there's a number type in JavaScript. It's not integral. It's always backed by a floating point type, and usually you can kind of get away with this because you can store most integers into 53 bits. But it turns out Beam uses a lot of integers that don't even fit into 53 bits. And so this poses a lot of other challenges, like the infinite past, the infinite future, the end of the global window. These are defined kind of to be the largest thing that fits into 64 bits, and JavaScript just can't handle that exactly. Can't even represent that exactly. So these are some of the downsides of using JavaScript. So let's dive into what an actual JavaScript pipeline looks like. TypeScript pipeline. So we have our we can create a function that is word count, and these functions, since functions are kind of first-class citizens, we say, well, let's just be able to use functions as if they were transforms. So you'll notice here that we just have a function word count, and then down below, we can apply this word count as if it was a p transform. No need to introduce this class hierarchy or anything like that. We just say any function that takes p collections, or really that takes any collection of p collections, can be used as a p transform. And then we can do map operations. So we have a map operation that just takes a lambda. In this case, this first map on the screen is taking a string and lowercasing it. Then we have a flat map operation. That's kind of the other quintessential operation. We take a string and we split it up into its parts. Similar to Python, we use generators. So this yield star means yield one at a time everything in this list. And then we have the apply operation that everyone is very familiar with, which applies a p transform. One notable departure is that we have added methods to p collections. So we took a very pure approach when we were going out with Beam. This was partly a reaction to Flume that had like 806 methods on the p collection to try to give it a more open feel. And we're kind of taking a step back a little bit and saying, we're going to be very careful and add certain operations. In this case, we've got map, we've got flat map, and there's a couple others that we're looking at that are directly on the p collection itself, just because they're so common. And then for everything else, you can apply, and you can apply an arbitrary pre-transform. So this is what it looks like. Now, another thing that we're leveraging in our TypeScript SDK is external transforms. So we're taking the approach, now we have this cross-language capabilities for Beam on the portability model. We don't have to do everything in JavaScript to have a usable JavaScript SDK. We can borrow all of the machine learning things from Python. We can borrow all of the IOs from Java. We can borrow SQL from Java, and we actually have that wrapped. So because you're interacting with an external system, as I mentioned, this async await thing is contagious. So you have to apply async, which returns technically a promise. But you're able to do kind of, bootstrap an SDK with a huge amount of existing features that are already in all the other SDKs. And we added the ability to automatically fetch and start expansion services. So this is, fairly easy to do. You can literally say SQL transform, and we'll go get the Java jar from the latest Maven repository, download it, start up Java, expand the SQL transform, and return it to you embedded as part of your JavaScript pipeline. Some other advanced features, and these are more experimental, where we're playing around to see exactly what we want to do here, is we have a more powerful p-value type. So you can say p-value and give it a list of p collections, or you can give it a JSON object of p collections, or a JSON object that has lists in it. And then you can apply a p transform to that. And this is, we don't have to introduce these notions of p collection lists and p collection tuples and all that kind of thing that we had to do in Java. We do support more advanced operations for maps. So if you want to have side inputs, if you want to inspect your windows, if you want to pass in other context, every map function takes the element and then the separate context object, which is just a JSON object you define down here outside the map. And so this is kind of how you can get the more advanced features. We support all our windowing semantics, so you can do different windowing. You have, if you're running on a runner that supports streaming, the TypeScript SDK supports streaming just out of the box. When I talked about relational things, for our grouping, instead of having to create key value types and then saying group by key, the basic operation we're exposing is a group by, and you say group by city. And what it does is, if your object is a JSON object that has a city field in it, we will use that city thing as the key. You can also group by a lambda. So you can group by element maps to the third part of element mod 3, and it will use that as the key. So this is more like kind of what you'd expect for SQL or relational. So there's not a special key field. You designate what you want to use as the key when you're doing your aggregation. And then for having multiple outputs, we're exploring new kinds of ways of doing things. So this map function is already fairly complicated. So we pulled that out and said, if you want to do multiple objects, what you can do is you can follow your map function with a split that then will split a single p collection. It'll partition into p collection in different ways. So you can partition a p collection on a field, So you can say look at this field, and every value of that field goes to a new P collection. Or you can say, I have a JSON object, and some of my things have A members, and some of my things have B members, and some of them have both. And I want to get the P collection of things with A members and the P collection of things with B members. And so we're using this new SDK to kind of explore new ideas of how we could represent the Beam model. So let's look a little bit on the other side of the SDK is once you've built up your pipeline, how do you actually execute this thing on a remote worker? So go ahead, Kerry.
So this is actually one of the largest challenges that we found inside TypeScript and JavaScript in general. So if we think of what we need to do to remotely execute that user code, we have to be able to package it, serialize it, and then transmit it through the pipeline so that it ends up on the worker, deserialize it, and execute it. This was my focus during the project, and we found it quite challenging because the notion of serializing with absolute fidelity arbitrary JavaScript objects was not well supported by JavaScript or TypeScript. This led me on a wild goose chase that I'll go into in a little bit to try and find out how we can do this effectively. This being a short-term hackathon project, we didn't have the luxury of diving deep and writing our own serialization library. Instead, we found some open source projects that implement some of the functionality we want. Each project that we chose, TS serialized chip closures and ES serializer, had some pros and cons. And we still don't have a working, for all our examples, end-to-end serialization. So this is something that needs further work, and we may have to bite the bullet and implement our own serialization for JavaScript and TypeScript.
I gave a talk on this a couple of years ago. There's a link here, so I'm not going to go into detail because that would be over an hour in and of itself. But the basic feature is you have these 4 services that you interact with to execute your pipeline. And whenever you're doing kind of out of process execution, out of process calls, you have to take efficiency into consideration. Because what you're doing is, if you made a remote procedure call for every single element you wanted to execute, for every single function in the foreign language, that's okay if you're doing, thousands or maybe millions. But Beam pipelines run over literally trillions or quadrillions of elements in their lifetime. And so every little bit of overhead that you can shave off there can actually be very big savings. So the way the protocol works is there's 4 services. The first is the control service. And when an SDK worker comes up, the first thing it does is it connects to the control service and it says, what work do you have for me to do? And the control service returns a chunk of work here represented by these hexagons of here's a bunch of UDFs that are all wired together, and this is what you need to execute. And then it says, okay, why don't you read from this little chunk of your input source and plumb those through and then give it back to me. So that's where the data channel comes in. This is the second item. So you might be executing multiple different UDFs, multiple different functions in parallel, and the runner will feed you data. And then what you do is you take that data, you run it through the appropriate UDFs, and then you kind of batch that data back to the runner. So there's this kind of back and forth that this data is continuously streaming to the SDK, and the results of the computations are continuously streaming back in a batched manner. The other side you have is there's this state service. So this is another data channel, but rather than being push-based, it's the things that need to be pull-based. So when you do state and timers, and also we use this for side inputs, what happens is the worker, the SDK, initiates the need for data. It says, I need to get the side input for this, or I need to do a state lookup for this. And it goes to the runner. The runner does whatever it does internally to get you the right data and gives it back to you so you can continue processing. The last service is just the logging service. This is so that when you log things in your SDK, they can get surfaced in the appropriate way to the runner, and that's pretty straightforward. You just shove logs along the channel. So these are the 4 kind of essential pieces that you need to implement on the worker side. So it turned out to be fairly straightforward to actually get all these up and running. If you look at it, it's under 2,000 lines of code, which I don't know if that speaks to the compactness of the service or the compactness of writing TypeScript, but is pretty decent. I will say that, in Java and Python, this is much, much more verbose. And part of it is due to the completeness, because we don't have progress yet, we don't have timers yet. So there are kind of some implemented features. And part of it's due to the fact that Java and Python evolved historically organically. The original SDKs didn't have any, portability wasn't even invented yet. So they were not as straightforward. But I think the JavaScript SDK, since we had portability from the get-go, is a good illustration of, like, if you're just targeting portability, how compact you can be. So you can kind of see there's a couple hundred lines of handling the data channel, a couple hundred lines of handling the state channel. The operators that build these graphs, there's 600 lines there. Pardue context is very specific to JavaScript. Every different one of the things you have to decide when you're building language is how are you going to represent these advanced do funds? If it's not just a single input in, single input out, use some more complex calling conventions. That is very specific to JavaScript, but overall not too bad in terms of writing an SDK from scratch. One of the bonuses that we had when we built this worker is we could actually use this to implement a direct runner very easily. So the work items that a worker actually executes very strongly resemble what a pipeline is. And this is no accident. We decided to use the same protocol representation for a work item tree as we did for the whole pipeline tree. And of course, there's some operations that you can't do locally on your worker. For instance, group by key, there may be other workers that have keys. But the good thing about this local worker is if you have exactly one bundle, exactly one worker, then anything you do for this worker is also being done globally for the pipeline. Just a sec. So if you want to do a group by key and you only have one bundle, you can just literally do a group by key by having a do fund that just has a grouping table. And once it's seen everything in this bundle, it's seen everything for the entire pipeline. The other, sorry. The other thing is there's the impulse function. The important thing about impulse is it happens exactly once across all workers. But if you have exactly one worker with exactly one bundle, it's easy to emit something exactly once across your entire pipeline. And so you throw these two different operations into your ability to execute the worker code, and you can actually implement the entire pipeline as a direct runner, just reusing 99% of the worker code. Also, I want to call out that this group by key, locally, is essentially the same operation that you want to do for the combine and group by key combiner lifting optimization. So this right here is even shared code with the production runner. This runner doesn't do unbounded, doesn't do streaming, doesn't do cross language, but it implements a huge portion of kind of what you'd want to test if you just want to test locally, try out your do funds and things like that. Whenever you want to run something that doesn't fit into this runner, you can always use the universal local runner or Flink or anything like that if you don't want to, and then you go on to a production service if you get to that point. But this is kind of a really big benefit of the way things are structured. You get kind of a direct runner for free. I do want to call it the one complication is side inputs. So side inputs required a little bit of rewiring. Traditionally, what happens is you have to have your side input completely materialized for the window in question before you execute your elements on your main input. And we had to do some rewriting to support side inputs. So what we did is we rewrote this into a form where we make the side input and the main input into the input into this kind of like buffering operation that only buffers things until all the inputs have come in. And this store operation that reads the side input, its edge into the buffering doesn't ever emit anything. It's just kind of a dependency edge to make sure that the side input is completely consumed before the buffer operation thinks it's done. And what it does is it actually just sticks things into an in-memory state. And then once everything from the main input and the side input has been consumed by the buffer releases everything to the downstream Pardue, which then does lookups into this in-memory state. This is the job that a runner would normally do, but we can build it right into the direct runner. And with this rewrite, you can now support side inputs. Once we have timer support in the SDK, I think there's probably a rewrite that would be a little bit similar to be able to support this. But side inputs, like once you have side inputs and you have view funds, map funds, and group by keys, kind of that's your bread and butter. So the direct runner can execute most pipelines, and then if you need something more, it's portable, so you can easily run on any other runner. So let's look at what's next.
So the biggest thing that I want to let everyone know is what's next is contributing this to the Beam repository. And so I'm doing that to get all of our code in, get it reviewed. And following that, what we need to do is expand and extend this. And for that, we need you, the Beam community. This is something where I think we have a great chance to involve the community, because as we've seen before, there are many, many, many JavaScript and TypeScript developers out there. And I think as a team, we are not the deepest or the richest in TypeScript and JavaScript functionality knowledge. And so by having contributions from you, the Beam community, we can make this a stronger, better, more idiomatic representation of JavaScript and TypeScript. And we can make this a full SDK. That's something that we have as a long-term goal. We could execute this much in a short time. We want to see what we can do to grow this project down the line with community support. And I think that's our talk. So we'd love to hear questions from y'all.